What if the strangest planet in our solar system isn't actually strange at all, and the only reason we thought it was broke down to a few hours of bad timing? For nearly 40 years, one brief flyby became the entire scientific record of an ice giant. No one questioned it until now. To understand what really happened, we have to look back at a single 6-hour flyby in 1986 and the solar storm that hit at exactly the wrong moment. What we find on the other side changes what we thought we knew about 5 moons we'd already written off. If the unknown is what keeps you watching, hit like and subscribe so you never miss what we uncover next. It helps us reach more people who think the way you do. We're genuinely glad you're here. Now, let's begin. Picture the solar system laid out on a single road, 1 kilometer long, with the sun at one end. Mercury, Venus, Earth, and Mars would all sit within the first 40 meters. Jupiter and Saturn would carry you out past 200 meters. And Uranus, the planet at the center of everything we're about to explore, wouldn't appear until you'd walked nearly 400 meters down that road. It orbits the sun at a distance of roughly 2 billion kilometers, almost 20 times farther out than Earth. Sunlight that reaches us in 8 minutes takes over 2.5 hours to reach Uranus. By the time it arrives, that sunlight carries about 400 times less energy than it does here. A day out there, lit by a sun reduced to a bright point, is a different kind of daylight altogether. A single orbit around that distant sun takes Uranus 84 Earth years to complete. If you were born the year Uranus passed a particular point in its orbit, you would need to live to extreme old age just to see it return to that same point. Entire human lifetimes pass while Uranus completes a single lap. And yet distance isn't what makes this planet strange. Every planet in the outer solar system is far away. What makes Uranus genuinely unlike anything else orbiting our star is the way it sits in space. Every other major planet spins more or less upright, like a top, with its axis roughly perpendicular to the plane it orbits in. Earth tilts about 23 degrees, Mars tilts about 25. Even Saturn, with its dramatic rings, only tilts about 27 degrees. Uranus tilts 97 degrees. That number is easy to read past, so slow down on it for a second. A 90-degree tilt would mean the planet's axis points directly into its orbital path, not up and down, but sideways. Uranus blows past even that. It doesn't lean, it lies down. Picture a spinning top that, instead of standing on the table, is rolling across it on its side, axis pointed almost exactly at whatever it orbits. That is Uranus, for its entire 84-year journey around the sun. The result is a planet with seasons unlike anywhere else in the solar system. For roughly 21 years at a stretch, one pole of Uranus points almost directly at the sun, while the other sits in unbroken darkness. Then, as the planet continues its slow orbit, day and night begin sweeping in stripes across the surface, the way they do on a normal planet, until 2 decades later, the poles swap, and the side that spent 21 years in darkness finally sees the sun again. A child born at the wrong pole in the wrong season could grow up, finish school, and start a career, all without ever seeing daylight. Nobody fully agrees on why Uranus ended up this way. The leading explanation, treated as a strong hypothesis rather than settled fact, points to a violent collision early in the solar system's history, something roughly Earth-sized, possibly larger, striking the young planet at just the right angle to knock it onto its side and never let it fully recover. It's a reasonable explanation. It is not a proven one. No spacecraft has ever orbited Uranus long enough to gather the kind of data that would settle the question for good. That's worth sitting with, because it's the central tension of everything that follows in this video. We are not talking about a planet science has thoroughly mapped. We are talking about a planet that, until extremely recently, science had glimpsed exactly once through a narrow window for a few hours decades ago. Everything we thought we understood about Uranus, every textbook diagram, every documentary narration, traces back almost entirely to that one encounter. There's one more piece of context worth having before we go back to that encounter, because it tells you something about how little this planet behaves the way distance alone would predict. Uranus holds the record for the coldest atmospheric temperature ever measured on any planet in the solar system, a minimum of about 49 Kelvin, or roughly minus 224 degrees Celsius, recorded in its upper atmosphere. That alone might not sound surprising for a planet this far from the Sun. What is surprising is that Neptune, sitting nearly 1.5 billion kilometers farther out, doesn't hold that record. Uranus does. The likely explanation has nothing to do with sunlight and everything to do with internal heat. Neptune radiates more than twice the energy it absorbs from the Sun, churning out heat from its own interior the way Jupiter and Saturn do. Uranus, almost uniquely among the giant planets, radiates barely any internal heat of its own at all, a deficit some scientists connect back to the same hypothesized ancient collision that knocked the planet onto its side in the first place, though that link too remains a working hypothesis rather than a settled conclusion. A planet that runs colder than its more distant neighbor, for reasons still not fully understood, is already a planet that doesn't behave the way simple distance from the Sun logic would predict. Keep that in mind, because it's a preview of a pattern you're about to see again and again in this story, a planet that keeps refusing to follow the rules astronomers expect it to follow. So let's go back to it. Let's go back to the only time a spacecraft from Earth has ever stood close enough to Uranus to look it in the eye. Uranus has only been part of human knowledge for a fraction of recorded history. Every planet visible to the naked eye, Mercury, Venus, Mars, Jupiter, Saturn, has been watched, tracked, and woven into mythology for thousands of years. Uranus was different. It sits right at the edge of naked eye visibility, faint enough that, for most of human history, anyone who happened to glance at it simply assumed they were looking at a dim, unremarkable star. That changed on the night of March 13, 1781, in a garden in Bath, England. An astronomer named William Herschel, German-born, trained as a musician, an amateur stargazer who built his own telescopes in his spare time, was working through a systematic survey of faint stars when he noticed something that looked wrong. Examining the stars near the constellation Gemini, he spotted an object that appeared visibly larger than the points of light around it, not a sharp pinprick like a star, but something with an actual, resolvable disk. He first assumed he'd found a comet and reported it as one to England's Astronomer Royal. It took months of careful observation by astronomers across Europe to settle the question. Comets move on long, stretched-out elliptical paths and trail visible tails. This object did neither. By the time its orbit was properly calculated, it was clear this wasn't a comet passing through, it was a planet, orbiting the Sun on a nearly circular path, twice as far out as Saturn, the most distant planet known at the time. It was, as multiple astronomical bodies would later confirm, the first planet discovered since antiquity, the first time in recorded human history that the known boundary of the solar system had moved. Herschel wanted to name his discovery after his king, calling it Georgium Sidus, George's star. The honor didn't survive contact with the rest of the astronomical world. Astronomers outside Britain pushed back against naming a planet after a living monarch, and the name that eventually stuck was Uranus. After the Greek god of the sky, continuing the old tradition of naming planets for mythological figures, though notably keeping the Greek name, rather than following the Roman pattern used for every other planet. What followed Herschel's discovery wasn't a flood of new knowledge. It was nearly 2 centuries of almost nothing. For 200 years after its discovery, astronomers on Earth knew little more about Uranus than the existence of 5 moons, all of them spotted gradually one by one. By telescope across more than a century and a half, Titania and Oberon, by Herschel himself in 1787, Ariel and Umbriel in 1851, and Miranda not until 1948. No rings were known to exist around the planet at all until remarkably recently. It wasn't until March 1977, just 6 months before Voyager 2 left Earth, that astronomers discovered Uranus had rings, and they found them almost by accident, watching the planet pass in front of a distant star and noticing the star's light flicker as unseen rings briefly blocked it. Sit with that timeline for a moment. Humanity knew a 7th planet existed for nearly 200 years before we had any direct evidence it had rings. We knew its 5 moons only as faint points of light, never as actual worlds with surfaces, geology, or history. Everything we now picture when we imagine Uranus, its pale blue-green color, its tilted rings, its strange moons, comes from a scientific record that is, in the grand scheme of the planet's history, astonishingly recent and astonishingly thin. And then, for one single afternoon in January 1986, that changed all at once. In the early 1970s, NASA's engineers noticed something that happens roughly once every 175 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were lining up in a way that would let a single spacecraft visit all 4, using a sequence of gravity assists, slingshotting from one planet to the next, instead of carrying enough fuel to power its own way across billions of kilometers. Miss that alignment, and the next opportunity wouldn't come again until the next century. NASA built 2 spacecraft to take advantage of it. Voyager 2 launched on August 20, 1977, 16 days before its twin, Voyager 1. The mission's primary objective was Jupiter and Saturn. Both spacecraft were guaranteed to reach those 2. Anything beyond that depended on whether the hardware kept working and whether mission planners chose to extend the trajectory rather than end the mission early. That decision wasn't automatic. The original Grand Tour concept, a single mission visiting all 4 outer planets, had been scaled back years earlier for cost reasons, replaced by a more modest plan that only guaranteed flybys of Jupiter and Saturn. Whether Voyager 2 would ever get the chance to continue on to Uranus and Neptune depended entirely on 2 things: the spacecraft surviving its first 2 encounters in working order, and Voyager 1 successfully completing its own priority objective at Saturn's giant moon Titan. If Voyager 1's instruments had failed to get a good look at Titan, mission planners were prepared to redirect Voyager 2 there instead, sacrificing Uranus and Neptune entirely to make sure at least one spacecraft captured Titan up close. Voyager 1 succeeded. Voyager 2 was released to keep going. Voyager 2 flew past Jupiter on July 9, 1979, and past Saturn on August 26, 1981. Both flybys succeeded. Voyager 1 had already completed its own close study of Saturn's giant moon Titan, which meant Voyager 2 was free. Engineers committed it to the long, uncertain road toward Uranus, with Neptune as a hoped-for bonus if the spacecraft survived that far. It would take almost 4.5 more years to get there. On January 24, 1986, at roughly 17:59 Universal Time, Voyager 2 made its closest approach to Uranus, passing within about 81,500 kilometers of the planet's cloud tops, roughly a fifth of the distance between Earth and the Moon. This was, and remains to this day, the only time any spacecraft built by humanity has ever visited this planet. not the only time recently, the only time, period. Every image, every magnetic field reading, every density measurement, every textbook fact about Uranus's interior traces back to data gathered in a window of just a few hours, using instruments designed in the 1970s, beaming information back to Earth at a rate slower than a modern dial-up modem. And here's where Uranus's sideways tilt stops being just a strange fact and starts shaping the entire encounter. Because the planet's axis pointed almost directly at the incoming spacecraft, Voyager 2's trajectory toward Uranus looked nothing like its approach to Jupiter or Saturn. At those planets, the rings and moons orbit roughly edge-on to an approaching spacecraft, spread out like a target you fly past from the side. At Uranus, with the whole system tipped on its side, Voyager 2 was flying almost straight into a bullseye, the planet dead center, its moons and rings circling around it like the rings of an archery target, rather than stretching out to either side. That geometry created a brutal time constraint. At Jupiter and Saturn, Voyager 2 had several days of close-range observation to work with. At Uranus, the approach geometry compressed that window down to roughly 5.5 hours of serious close study. Whatever the spacecraft was going to learn about this planet, it had to learn it almost entirely in that single afternoon. It almost didn't get the chance. On January 18, just 6 days before closest approach, Voyager 2 began transmitting images that came back badly streaked, corrupted by a fault in the system responsible for compressing image data before transmission. Engineers on the ground traced the problem and uploaded new instructions to route around the faulty component. Normal images started coming through again on January 21, 3 days before the flyby that would define our understanding of this planet for the next 40 years. Light was another obstacle. At Uranus's distance, sunlight carries roughly 400 times less intensity than it does at Earth, and slightly more than half of what reaches Saturn. Every photograph Voyager 2 took demanded exposure times long enough that the spacecraft's own motion threatened to blur the image, forcing engineers to program precise image motion compensation into the onboard computer just to bring back anything usable. Despite all of it, the corrupted imaging system, the impossibly short window, the faint and distant light Voyager 2 delivered, it returned close to 7,000 photographs. It discovered roughly 10 new moons orbiting the planet, including one, later named Puck, spotted in the final approach before closest encounter, discovered while the spacecraft was still inbound. It found 2 entirely new rings in addition to the 9 already known from ground-based observation. It imaged the 5 large moons already known to astronomers, Miranda, Ariel, Umbriel, Titania, and Oberon, in enough detail to reveal canyons, fault systems, and surface features no telescope on Earth could ever have resolved. And then it found something nobody expected to find at all, a planet with a magnetic field unlike any other world humanity had ever measured. That discovery is where this story actually begins. Before Voyager 2 arrived, scientists didn't actually know for certain that Uranus had a magnetic field at all. Every other giant planet visited up to that point, Jupiter, Saturn, had one. Generated the way Earth's is presumed to be generated, through a dynamo process deep in a planet's interior, where the convective motion of an electrically conductive fluid, molten metal on Earth, metallic hydrogen on Jupiter and Saturn, generates a magnetic field roughly aligned with the planet's spin axis. It was a reasonable assumption that Uranus would follow the same pattern, just smaller, just colder, just farther away. The instruments on board Voyager 2 found a field. They confirmed that immediately. What took longer to process, what genuinely puzzled the scientists analyzing the data afterward, was the shape of it. On Earth, on Jupiter, on Saturn, a magnetic field behaves roughly like the field around a bar magnet sitting near a planet's center, aligned closely with its axis of rotation. You can predict where the magnetic poles will be because they sit close to the geographic poles. Uranus broke that pattern completely. The magnetic field detected by Voyager 2 was tilted roughly 59 degrees away from the planet's actual rotation axis. Not a small wobble, but an enormous, almost perpendicular divergence between the axis the planet spins on and the axis its magnetic field points along. On top of that tilt, the entire field was offset from the planet's geometric center by roughly a third of Uranus's radius, shoved off-axis, in a way none of the other giant planets displayed. Picture spinning a globe with a bar magnet buried somewhere inside it, except instead of placing that magnet through the center, pointing along the poles, you've shoved it off to one side and tilted it almost sideways relative to the spin axis. Now spin the globe. The magnetic field sweeping through space around it wouldn't behave like a clean, predictable shape anymore. It would wobble, twist, and vary wildly in strength depending on where you measured it, because the geometry generating it has nothing to do with the simple, centered picture that works for Earth or Jupiter. The numbers Voyager 2 returned reflected exactly that chaos. As the spacecraft approached, its instruments detected a bow shock, the boundary where the solar wind first slams into and is deflected around a planet's magnetic field at a distance of roughly 23 Uranus radii from the planet. Closer in, they cross the magnetopause, the actual boundary of the magnetic field itself, at about 18 Uranus radii, and near closest approach, the instruments recorded a peak magnetic field strength of 413 nanotesla at a distance of roughly 4 Uranus radii from the planet's center, a field comparable in overall strength to Earth's, but distributed so unevenly across the planet that comparing the two is almost meaningless. Because the field is both tilted and badly off-center, its strength varies enormously depending on where around the planet you measure it, strong in some regions, startlingly weak in others, in a way that simply doesn't happen at Earth, Jupiter, or Saturn. Scientists studying the data afterward proposed an explanation, one that remains the leading hypothesis today rather than a confirmed fact, that Uranus's magnetic field isn't generated deep in a metallic core the way Earth's or Jupiter's is, but instead at an intermediate depth inside the planet. In a layer where extreme pressure makes water electrically conductive enough to sustain a dynamo. If that's correct, it would help explain why the field looks so different, generated in a messier, shallower, less symmetric layer than the deep metallic interiors that produce clean, centered fields elsewhere in the solar system. It's a compelling idea. It has not been confirmed by direct measurement because no instrument has ever been sent back to take one. Think about what that means for something as basic as a compass. On Earth, a compass needle works reliably almost anywhere on the surface because the magnetic field beneath you is centered and predictable, point toward magnetic north, and that direction stays roughly consistent no matter where you're standing. On Uranus, that same simple tool would be close to useless. Stand in one location, and the field might point you in something resembling a sensible direction. Move a relatively short distance, and the chaotic, off-center geometry of the field could send the needle swinging toward a completely different bearing, because you're no longer the same distance from a magnetic axis that doesn't even run through the planet's center. There may be no single, true north on Uranus in any meaningful sense, just a magnetic environment that shifts depending on exactly where, and exactly when you happen to be measuring it. There was a second anomaly buried in the data that took scientists even longer to make sense of, and it concerned something that should have been a footnote: the radiation belts. Every planet with a strong magnetic field is expected to trap charged particles from the solar wind into donut-shaped radiation belts circling the planet, the way Earth's Van Allen belts do. Given the strength of the magnetic field Voyager 2 measured, researchers expected to find proton radiation belts of a predictable intensity around Uranus. What they found instead were belts roughly 100 times weaker than the upper limit their models predicted. Not absent, just oddly, dramatically faint, as if something was actively preventing particles from accumulating the way physics said they should. For decades, that gap between prediction and observation sat largely unresolved, one of several strange, loose threads left behind by a 6-hour encounter that nobody had the means to go back and double-check. Because here is the part that should unsettle you a little. Every one of these numbers, the 59-degree tilt, the off-center, offset, the 413 nanotesla peak, the oddly faint radiation belts, comes from a single set of instruments operating for a few hours. On one specific day in January 1986, Uranus has been orbiting the Sun for over 4.5 billion years. Voyager 2 looked at it for an afternoon. And from that afternoon, an entire scientific consensus was built about what kind of planet this is, what its magnetic field permanently looks like, and what that implies about its interior, its moons, and its potential to support anything resembling habitable conditions. That consensus held for almost 40 years. Nobody seriously challenged the basic picture because nobody had new data to challenge it with. But there was one more piece of that 1986 dataset, stranger than the tilt, stranger than the offset, that took scientists over 3 decades to even notice. It was sitting quietly in the spacecraft's magnetometer readings the entire time, overlooked, until a research team went back and looked again. For more than 30 years after Voyager 2's encounter with Uranus, the raw magnetometer data from the flyby sat archived, available to anyone who wanted to study it, largely unexamined for anything beyond the broad conclusions already published. Then in 2020, a team of researchers at NASA's Goddard Space Flight Center went back through the old readings, applying analysis techniques and models that simply didn't exist in 1986, looking for anything the original investigation might have missed. They found something. Buried in a brief blip in the magnetometer data, a signature lasting only a few minutes during the flyby, was evidence of what's called a plasmoid, a detached bubble of magnetized plasma pinched off from the planet's magnetic field and flung away into space, carrying a portion of the planet's own atmosphere along with it. This is not a hypothetical phenomenon dreamed up to explain a strange reading. Plasmoids are a well-documented mechanism by which planets with magnetic fields lose atmosphere to space, and they've been observed at both Jupiter and Saturn. What made the Uranus plasmoid worth a second look wasn't that it existed, it was the company researchers found it keeping. Where the plasmoids seen around Jupiter and Saturn tend to be twisted, irregular structures shaped by the violent, turbulent magnetic environments those giant planets generate. The structure researchers identified in the Uranus data appeared to be a clean, closed loop, a simpler, more orderly shape than anything seen at the other gas giants, consistent with the unusually lopsided magnetic environment Voyager 2 had already revealed. And the scale of what that single, brief detection implied was startling. Voyager 2 only happened to pass directly through this one plasmoid for a matter of minutes during a flyby lasting a matter of hours. Researchers compared the experience to a single aircraft flying once through a small patch of one country's weather, and trying to characterize the climate of an entire continent from that one pass. If that one detected plasmoid was representative of how often this kind of event happens at Uranus, and there's no way to know for certain. From a single sample, then this mechanism alone could account for somewhere between 15 and 55% of the total atmospheric mass Uranus loses to space. That's an extraordinary range of uncertainty, and it exists precisely because we have exactly one data point, one plasmoid, one brief window. One 6-hour flyby, decades ago, that still defines the entire boundary of human knowledge about how this planet loses pieces of itself to the vacuum around it. Put the three anomalies side by side, and a pattern starts to emerge that goes well beyond Uranus is an unusual planet. The magnetic field tilted almost perpendicular to the rotation axis. Radiation belts 100 times fainter than predicted. An atmosphere apparently leaking away through plasma bubbles whose true frequency nobody can pin down. 3 separate puzzles, each one resting on the exact same shaky foundation, a handful of hours of data, gathered once, never independently confirmed. It helps to put that atmospheric loss in context, because losing atmosphere to space isn't unusual in itself. Every planet does it to some degree. What matters is the mechanism and how much control a planet has over the process. Venus and Mars have no global magnetic field of their own, which means they have essentially no protection at all. The solar wind strikes their upper atmospheres directly and strips material away continuously, a slow bleed with no shield in the way. Earth, by contrast, is wrapped in a strong, well-centered magnetic field generated deep in its molten core, and that field deflects most of the solar wind before it ever reaches the atmosphere, which is a large part of why Earth has kept a thick, breathable atmosphere for billions of years, while Mars unprotected. Lost most of its own, Uranus sits in a strange middle category that none of those planets occupy. It does have a magnetic field, strong in places, by some measures comparable to Earth's. But because that field is wildly tilted and badly off-center instead of clean and centered, it doesn't form the kind of uniform shield Earth's does. Instead, the lopsided geometry appears to create exactly the right conditions for plasmoids, those detached bubbles of magnetized plasma, to pinch off and carry atmosphere away in irregular, hard-to-predict bursts. It's not the open, unshielded bleed happening at Venus and Mars, and it's not the well-defended stability of Earth. It's a third pathway, specific to a planet whose magnetic field is broken in a very particular way, and Uranus may be the clearest example of it anywhere in the solar system. For most of the history of planetary science, that was simply accepted as the unavoidable cost of studying somewhere this far away. Uranus orbits nearly 20 times farther from the Sun than Earth does. Sending another spacecraft there is an enormous undertaking, and for decades it sat low on the list of scientific priorities, overshadowed by missions to Mars, to Jupiter's moons, to Saturn's rings. But here's the question that should be sitting with you by now, the one this video is actually built around. What if the reason Uranus looked so anomalous in 1986 wasn't really about Uranus at all? What if it was about exactly when Voyager 2 happened to arrive? Because the Sun doesn't behave the same way every day. It has weather of its own, storms, eruptions, fluctuations in the stream of charged particles it constantly throws out into the solar system. A spacecraft's instruments don't measure a planet in isolation. They measure a planet immersed in whatever conditions the Sun happens to be producing at that exact moment. And in January 1986, conditions at Uranus may not have been ordinary at all. That possibility that the defining dataset of an entire planet might have captured not Uranus as it normally exists, but Uranus on one unusually disturbed day, is what a team of researchers set out to test decades later. By going back to data everyone assumed had already told its whole story, what they found didn't just add a footnote to the Voyager 2 encounter, it threatened to rewrite it. That's where we're headed next. Before we get to the discovery that reframes everything from Part 1, we need to spend time with the 5 worlds that Discovery is really about, because this is, underneath everything else, a story about moons. Over the past 2 decades, the search for life beyond Earth has quietly shifted its center of gravity. For most of the 20th century, that search focused overwhelmingly on planets, worlds with a solid surface, sitting in some star's temperate zone, warmed just enough by their sun to keep water liquid. But some of the most compelling candidates for life beyond Earth turned out not to be planets at all. Their moons, small, icy, orbiting far from any star's habitable warmth, kept liquid on the inside not by sunlight but by tidal flexing, the gravitational kneading of a much larger planet pulling and releasing them with every orbit. Europa, orbiting Jupiter, is now considered one of the single most promising places in the solar system to search for microbial life, precisely because of the ocean believed to exist beneath its icy shell. Enceladus, a small moon of Saturn, has been observed directly venting plumes of water vapor from cracks near its south pole, physical proof of a liquid interior reaching space itself. Uranus has 5 moons roughly comparable in size and composition to those icy worlds. And for nearly 40 years, the scientific consensus treated every one of them as almost certainly dead. Uranus has 28 known moons today, but for most of the 20th century, astronomers only knew of 5: Miranda, Ariel, Umbriel, Titania, and Oberon. Discovered one at a time by telescope, over more than a century and a half each one, nothing more than a faint point of light with no visible surface, no confirmed geology, no way to know what they actually looked like up close. The discoveries themselves stretch across an almost absurdly long span of time for 5 objects orbiting the same planet. Titania and Oberon came first, spotted by William Herschel himself in 1787, just 6 years after he discovered Uranus in the first place. More than 6 decades passed before Ariel and Umbriel were found, in 1851, by the English astronomer William Lassell, and then nearly another full century went by before Miranda, the innermost and smallest of the 5, was finally detected in 1948 by the Dutch-American astronomer Gerard Kuiper, a discovery that came only after telescope technology had advanced enough to pick out something that faint, that close to the glare of the planet it orbits. 3 separate astronomers, working across 3 different centuries, slowly assembled a family of 5 worlds that nobody would actually see up close until a single afternoon in January 1986. Voyager 2 changed that in a single afternoon, the same afternoon it rewrote everything we understood about Uranus's magnetic field. What it found was strange enough to reshape planetary science's picture of icy moons in general. Miranda, the smallest and innermost of the 5, turned out to be one of the most bizarre objects Voyager had photographed anywhere in the solar system. Its surface is a patchwork of wildly different terrains stitched together, smooth, young-looking plains sitting directly beside ancient, heavily cratered ground, cut through by enormous oval-shaped formations called coronae, flanked by fault scarps plunging as deep as 20 kilometers, roughly 20 times the depth of the Grand Canyon. Nothing about Miranda's surface looks like it belongs to a single coherent history. One leading explanation, again, a hypothesis rather than a settled fact, suggests Miranda may have been shattered by a violent impact earlier in its history, and then gravitationally reassembled itself, leaving pieces of its interior stitched back together on the outside in no particular order. Scientists nicknamed it, only half-jokingly, the Frankenstein moon. One feature on Miranda deserves particular attention because it captures just how strange this small moon really is. Among the fault scarps Voyager 2 photographed is a cliff named Verona Rupes, standing roughly 20 kilometers from top to bottom, more than double the height of Mount Everest measured from sea level, and quite plausibly the tallest cliff anywhere in the solar system. Because Miranda's gravity is so weak, barely a fraction of a percent of Earth's, an object dropped from the top of Verona Rupes would fall for nearly 12 minutes before reaching the bottom, eventually striking the surface at a survivable speed of roughly 200 kilometers per hour. No atmosphere to create drag, just an extraordinarily long slow-motion plunge in near-total silence. And even that image comes with an asterisk worth sitting with. During the flyby, Miranda's southern hemisphere happened to be angled toward the sun, which meant Voyager 2's cameras could only usefully photograph that one half of the moon. The entire northern hemisphere of Miranda, everything on the far side of whatever line divided day from permanent shadow that particular week, has never been imaged by any spacecraft at any resolution in the history of space exploration. Half a world, entirely unseen. Ariel, the next moon out, told a different story. Voyager found it covered in long fault valleys and what looked like frozen flows of icy material, evidence pointing toward some kind of past geological activity, cryovolcanism, ice behaving the way lava behaves on a rocky world, erupting and resurfacing the ground around it. Of all 5 major moons, Ariel appeared to have the brightest, youngest-looking surface, suggesting whatever resurfaced it had happened relatively recently in geological terms. But there's a critical limitation buried in that observation, one that matters enormously for what comes later in this story. Voyager 2's flyby geometry meant it only ever imaged roughly 35% of Ariel's surface. Nearly 2/3 of this moon has never been photographed by any spacecraft at any resolution at all. Umbriel, by contrast, looked almost the opposite of Ariel, an old, dark, heavily cratered surface with little obvious sign of recent activity, the kind of moon that appeared, at least from what little Voyager managed to see, geologically frozen in time. It's the darkest of Uranus's 5 major moons, reflecting less than half as much sunlight as Ariel does, a surface so uniformly dim that scientists still don't have a confirmed explanation for it. The one striking exception is a mysterious bright ring of material, roughly 140 kilometers across, sitting on the floor of a crater named Wunda near the moon's equator, possibly an impact deposit, possibly a patch of pure carbon dioxide ice trapped in an unusually cold spot on the surface. Nobody knows for certain because, like so much else about these moons, it was observed exactly once, from one angle, in one lighting condition, and never seen again. Voyager 2's images only ever mapped about 40% of Umbriel's surface. Titania, the largest of the 5, showed huge fault systems and canyon networks suggesting some history of tectonic activity, cracks in its crust hinting the moon may once have been geologically alive in its interior. Some of Titania's canyons stretch for over 1,500 kilometers, longer than the length of California, evidence of crustal stresses that would have needed to pull the moon's icy shell apart at some point in its past. Oberon, the outermost of the 5 major moons, appeared similarly old and cratered. With hints of canyon-like features and at least one unusually tall, isolated mountain rising from its surface, but far less detail, resolved than for its inner siblings simply because Voyager's trajectory carried it past Oberon at a much greater distance at lower resolution with less time to observe. 5 moons. 5 very different stories, glimpsed for a matter of hours each, through instruments and imaging systems built with 1970s technology. And then, layered on top of those individual portraits, there was the far bigger and stranger puzzle from Chapter 3. The magnetosphere surrounding all 5 of these moons appeared to be almost completely empty of plasma. That emptiness should not have made sense. Icy moons orbiting inside a planet's magnetosphere are expected to interact with it constantly. Radiation and charged particles striking an icy surface knock water molecules loose, which get ionized and swept up into the surrounding magnetic environment, the same basic process that fills the plasma-rich environments around Jupiter's and Saturn's icy moons. If Uranus's 5 major moons were doing anything geologically or chemically interesting, if they were shedding even small amounts of material into space, some trace of it should have shown up in Voyager's instruments as it threaded through their orbits. It didn't. The plasma readings came back essentially empty. And so, working from the only data anyone had, scientists reached the most logical conclusion available to them. The moons must be inert, dead worlds, ancient, frozen, geologically silent, nothing coming off their surfaces because nothing was happening inside them to push anything off. That conclusion held for decades, not because the evidence was overwhelming, but because it was the only evidence anyone had, and nobody had gone back to double-check it. Except one detail should have raised more suspicion than it did at the time. Voyager 2 didn't just observe the moons quietly orbiting an ordinary magnetosphere. It observed them orbiting the same anomalous, chaotic magnetic environment described back in Chapter 3, a field wildly tilted, badly off-center, wrapped around a magnetosphere that already looked nothing like Jupiter's or Saturn's. If the environment surrounding these moons was itself behaving strangely during the flyby, was it really safe to assume the moons themselves were being observed under normal conditions? Nobody seriously pursued that question for years. It took a scientist with a very specific, very unusual piece of prior experience to go back and ask it properly. James JWST is a space plasma physicist at NASA's Jet Propulsion Laboratory. Before turning his attention to Uranus, he spent years working on data from a very different mission, Messenger, the spacecraft that spent 4 years in orbit around Mercury, the innermost planet of the solar system, completing thousands of individual orbits between 2011 and 2015. Mercury has its own magnetic field. Far weaker than Earth's, and over the course of those thousands of orbits, Messenger's instruments occasionally caught something remarkable, moments when intense activity from the sun completely overwhelmed Mercury's modest magnetic field, briefly erasing it, stripping the planet of its protective bubble entirely before conditions settled and the field reasserted itself. What made that pattern visible at Mercury and essentially invisible at Uranus for so long comes down to something simple: repetition. Messenger didn't fly past Mercury once. It orbited the planet for years, gathering thousands of individual snapshots of the same magnetic environment under wildly different solar conditions, which meant scientists could directly compare a calm day to a disturbed one and see, unambiguously, how dramatically the sun could reshape a planet's magnetosphere. Uranus never had that luxury. It had exactly one snapshot. There was nothing to compare it against, no second data point to reveal that the first one might have been unusual, which is precisely why an anomaly hiding in plain sight, of the kind JWST had learned to recognize at Mercury, could sit undetected in the Uranus data for nearly 4 decades. That experience left Jasinski with a specific kind of professional instinct, an awareness that a planet's magnetic environment is not a fixed, unchanging thing. It's a live system, constantly pushed and reshaped by whatever the sun happens to be doing at any given moment. A spacecraft doesn't measure a planet's magnetosphere in some pure, isolated state. It measures whatever that magnetosphere happens to look like at the specific instant it flies through, and if the sun is having an unusually active day, that instant might look nothing like the planet's typical condition. When Jasinski turned his attention to the decades-old Uranus dataset, that instinct produced an obvious question, one that, remarkably, nobody investigating Uranus's magnetosphere had rigorously pursued before. What if Voyager 2 simply caught Uranus at the wrong moment? What if the extreme magnetosphere that had defined this planet's scientific reputation for almost 40 years wasn't actually typical of Uranus at all, but a temporary state, triggered by conditions in the solar wind that happened to be unusual on that particular January afternoon in 1986? To test the idea, Jasinski and his colleagues went back into Voyager 2's own instrument data, not just the readings taken during the few hours of closest approach, but the full record of solar wind measurements the spacecraft had been quietly collecting for months before it ever reached Uranus. As it cruised through the outer solar system on its approach trajectory, in total, they analyzed roughly 8 months of solar wind data surrounding the encounter. Looking specifically at how the pressure and density of the solar wind upstream of Uranus behaved in the days and weeks leading up to the flyby, a baseline nobody had bothered to systematically reconstruct before, because for decades, nobody had seriously questioned whether the flyby conditions were representative in the first place. What they found, buried in data that had been sitting in archives for nearly 40 years, was the answer to a question almost nobody had thought to ask. Picture it this way. A planet's magnetosphere behaves a little like an inflated balloon, held at a certain size by a rough balance between two opposing pressures, the planet's own magnetic field pushing outward and the solar wind pressing in from outside. Under calm conditions, that balance settles into a stable, predictable shape. Squeeze the balloon suddenly from an unexpected direction, and everything inside gets compressed into less space, forced together, disturbed. Any plasma drifting loosely inside that boundary doesn't just sit there passively as the walls close in. It gets swept along, pushed outward and away, some of it likely escorted straight out of the system entirely as the compressed boundary sweeps past it. And whatever charged particles remain trapped inside closer to the planet get compacted and re-energized by the same violent squeeze, exactly the kind of process that could plausibly explain why Voyager 2 found a nearly empty magnetosphere, and at the same time, unusually intense radiation belts, 2 readings that had seemed contradictory for decades suddenly explainable as 2 symptoms of the exact same brief violent event. 2 weeks before Voyager 2 reached Uranus, the solar wind pressure upstream of the planet was low, unremarkable, ordinary, nothing that would have distorted the picture of the planet's magnetic environment in any dramatic way. Then, in the days immediately before the spacecraft's closest approach, something changed. The dynamic pressure of the solar wind slamming into Uranus's magnetosphere spiked by a factor of roughly 20 times. Not a gradual drift, not a modest fluctuation, a sudden, dramatic surge in the force of charged particles pressing in against the planet's magnetic field, arriving in almost the exact window Voyager 2 happened to be making its approach. The effect on Uranus's magnetosphere was immediate and severe. Under typical conditions, researchers estimate the sunward boundary of Uranus's magnetic field, the point where it holds the solar wind at bay, sits somewhere around 28 to 29 times the planet's radius from its center. In the days before Voyager 2 arrived, that boundary had already started somewhere in that normal range. By the time the spacecraft made its closest approach, the incoming pressure had squeezed that boundary inward to roughly 17 Uranus radii, compressing the entire magnetosphere down to something like 1/5 of its ordinary volume. Picture a protective bubble around a planet, suddenly squeezed down to a fraction of its usual size by an invisible wave of pressure from 93 million miles away. Everything inside that bubble, the radiation, belts the plasma environment. The space immediately surrounding the 5 major moons would have been violently reshaped by that compression, compacted into a smaller volume, its particle populations disrupted and redistributed in ways that had nothing to do with Uranus's ordinary steady-state behavior. Jasinski and his team didn't stop at identifying the compression. They wanted to know how unusual this event actually was, whether Voyager 2 had simply caught Uranus on a slightly above-average day, or whether it had witnessed something genuinely rare. Using the full 8 months of solar wind data surrounding the encounter as their baseline, they calculated how often conditions as extreme as the ones present during the flyby actually occur. That baseline mattered enormously to the credibility of the result. Without it, a single compressed reading proves nothing on its own. It's only by comparing that one moment against months of ordinary conditions that a rare event can be distinguished from a routine one, the same basic logic that lets a doctor recognize a fever as abnormal only because they know what a normal temperature looks like first. The answer, less than 5% of the time, by some estimates in their analysis, closer to 4%. Voyager 2, humanity's only spacecraft ever to visit this planet, arrived during the single most intense solar wind compression event in the entire 8-month window the researchers examined, a period that, by their own description, appeared to capture the peak of unusual solar activity surrounding the entire encounter. If Voyager 2 had arrived just a few days earlier, Jasinski explained after the study's publication in November 2024, in the peer-reviewed journal Nature Astronomy, it would have observed a completely different magnetosphere at Uranus. Had the spacecraft's trajectory carried it past the planet even a week sooner, a genuinely tiny margin against a mission that had already traveled for 8.5 years and billions of kilometers to get there, it would have encountered a magnetosphere roughly 5 times larger. In a solar wind environment 20 times calmer, producing a dataset that might have looked entirely unremarkable by comparison to Jupiter's or Saturn's. Every defining anomaly from Chapter 3 of this story suddenly has a second possible explanation. The vacuum magnetosphere, almost entirely devoid of plasma, potentially not evidence of 5 inert, geologically dead moons, but a temporary side effect of the solar wind compression violently sweeping plasma out of the system in the days before Voyager 2 arrived. The unusually intense electron radiation belts, the second most extreme ever measured around any planet in the solar system, potentially not a permanent feature of Uranus's environment, but a burst of energized particles injected into the belts by the same compression event, dissipating again once conditions return to normal. None of this proves the moons are active. That's an important distinction and worth stating plainly rather than glossing over. Jasinski's study doesn't claim to have discovered evidence of geological activity on Miranda, Ariel, Umbriel, Titania, or Oberon. What it demonstrates is something more foundational and, in a way, more unsettling, that the absence of evidence recorded by Voyager 2 might not have been evidence of absence at all. the moons could have been quietly producing water ions the entire time. The way icy moons around other giant planets do, and Voyager 2 simply arrived during the one window in 25, when a solar storm had already swept that evidence away before the spacecraft's instruments ever had the chance to detect it. Carol Patey, a planetary scientist at the University of Oregon who was not involved in the study, offered a measured assessment when the findings were published. This reanalysis doesn't hand us a complete explanation for every strange reading Voyager 2 returned. What it does is remove the ground from underneath 4 decades of assumptions. The quiet, largely unexamined premise that the 1986 flyby had captured Uranus as it typically exists, rather than Uranus caught in the middle of one of its least typical moments. Linda Spilker, Voyager 2's project scientist at JPL, put it even more directly. This finding will change how the mission's legacy is understood, not by discrediting the data Voyager 2 collected. Every measurement it made was real, accurate, faithfully recorded, but by exposing exactly how much weight the scientific community had unknowingly placed on a single, narrow slice of time, treated for nearly 40 years as though it represented the whole picture. There's a specific, concrete implication buried in this reanalysis that connects directly back to the 5 moons from Chapter 5, and it's worth spelling out clearly. Researchers had long assumed that Uranus's outermost large moons, Titania and Oberon, spend much of their orbit outside the planet's magnetosphere entirely, too far out to be meaningfully shielded, and therefore poor candidates for the kind of magnetic induction detection that has helped identify subsurface oceans on moons like Europa. But if the magnetosphere Voyager 2 measured was compressed to a fraction of its usual size, then the boundary of that magnetosphere was, during the flyby, sitting much closer to the planet than it typically does, under normal uncompressed conditions. The magnetosphere may extend far enough to routinely enclose Titania and Oberon after all, which would mean both moons are better candidates for hosting detectable subsurface oceans than anyone previously believed, simply because the one flyby humanity has ever conducted happened to catch the magnetosphere at its smallest. Interestingly, evidence pointing in the same general direction had already started surfacing before Jasinski's reanalysis was even published, not from Voyager's old data, but from an entirely different instrument, looking at an entirely different moon. In July 2024, a research team using the James Webb Space Telescope reported something unexpected on the surface of Ariel: thick deposits of carbon dioxide ice, concentrated heavily on the moon's trailing hemisphere, along with the first clear detection of carbon monoxide ice anywhere on its surface. Neither compound should persist there. At Ariel's distance from the Sun and its correspondingly frigid surface temperature, exposed carbon dioxide should slowly sublimate away into space over time, and carbon monoxide is even less stable, requiring temperatures colder than anything recorded on Ariel's surface to remain frozen at all. Finding either compound in any meaningful quantity implies something is actively replenishing it, and one of the leading candidates researchers proposed was material leaking up from Ariel's interior, potentially from a subsurface liquid ocean. Working its way to the surface through networks of grooves and fractures already visible in the Voyager 2 images from 1986, that JWST detection, on its own, doesn't prove Ariel has an ocean. Researchers were careful to note that competing explanations exist: radiolysis, the breakdown of surface material by charged particles from Uranus's magnetosphere, could also generate some of the same compounds without requiring any interior activity at all. But taken together with Jasinski's magnetospheric reanalysis, the two findings point in a strikingly similar direction, discovered independently, using completely different instruments, separated by decades of data collection. The 5 moons Voyager 2 quietly filed away as geologically dead in 1986 may deserve a second, much closer look. A separate 2024 study focused specifically on Miranda proposed that orbital resonances earlier in its history, periodic gravitational tugging from its neighboring moons, could have generated enough internal tidal heating to sustain a subsurface ocean one that plausibly could still exist today hidden beneath that famously chaotic Frankenstein-stitched surface. For a story about a magnetosphere, that would already be a remarkable turn, but the real weight of this discovery isn't really about magnetic field lines or plasma density measurements. It's about what those 5 moons might actually be, and whether the version of them we've been picturing for 40 years, frozen, silent, and geologically dead, was ever anything more than an accident of bad timing. None of this constitutes proof. It's worth restating that plainly, one more time, before moving forward. Nobody has directly detected an ocean beneath Ariel, or Miranda, or Titania, or Oberon. What's accumulated instead is something more modest but still significant, a set of independent findings, a magnetospheric reanalysis, a JWST spectroscopy study, an orbital dynamics model, that all point toward the same uncomfortable possibility arrived at from different directions, using different instruments built by different research teams who weren't necessarily working together. When separate lines of evidence, gathered independently, start converging on the same conclusion, that's usually the moment a scientific field starts paying closer attention. Consider, too, what it would actually mean if even one of these 5 moons turns out to host a genuine subsurface ocean. It would place Uranus in an entirely different category of planetary system, not just an oddly tilted ice giant with a lopsided magnetic field, but the anchor of a miniature solar system, potentially containing multiple ocean worlds orbiting in near-total darkness, 20 times farther from the Sun than Earth. Kept liquid not by starlight, but by the slow, patient churn of tidal forces and radioactive decay deep in each moon's interior. That's not a minor addendum to the story of this planet. That's a genuinely different story, one where Uranus stops being the answer to a magnetic field mystery and starts being a candidate location in the search for life beyond Earth. It's also, not coincidentally, exactly the moment a new mission becomes hardest to justify skipping. Uranus is not actually unique in facing this problem. It's simply the most extreme example of a challenge that runs through much of planetary science. Before Messenger settled into orbit around Mercury in 2011, humanity's entire understanding of that planet rested on 3 brief flybys by a single spacecraft. Mariner 10 back in the mid-1970s, and those flybys, by sheer bad luck of orbital timing, managed to photograph the same half of the planet's surface 3 separate times, leaving the other hemisphere completely unmapped for decades. Pluto's entire close-up scientific record still consists of a single flyby, by New Horizons, in July 2015, a few hours of data that, much like Voyager 2 at Uranus, now stands in for an entire world, indefinitely, until or unless another mission is ever sent, even Mars. One of the most thoroughly studied planets in the solar system today spent its first several decades of exploration known to humanity only through a handful of brief flybys before orbiters and landers began accumulating the kind of long-term repeated observation that reveals a planet's actual range of behavior rather than a single frozen moment of it. What makes Uranus different is the scale of the gap. Mercury eventually got its long-term mission. Messenger's 4 years in orbit turned 3 narrow, repetitive glimpses into a genuinely 3-dimensional picture of the planet, including the eventual discovery of ice hiding in permanently shadowed craters near its poles, a finding no flyby could ever have made. Mars got dozens of missions, spread across 60 years, enough repeated observation that scientists can now track its seasons, its dust storms, its climate shifting year over year rather than guessing at a single frozen snapshot. Uranus, despite being an entire class of planet, an ice giant. A category that, as far as astronomers can tell from surveying planets around other stars, may be the single most common type of planet in the galaxy, has had exactly one visitor for 5.5 hours during a solar storm 38 years ago. Every conclusion drawn about this entire category of world, anywhere in the universe, still traces back, in no small part, to that one afternoon. That last point is worth sitting with for a moment, because it reaches well beyond this one planet. If Uranus and Neptune really are representative of the most common type of planet orbiting other stars, more common than gas giants like Jupiter, more common than rocky worlds like Earth, then everything scientists think they understand about that entire category of planet across the galaxy still rests. At its foundation, on a single brief, possibly unrepresentative encounter with one of only 2 examples humanity has ever had the chance to study up close. Get Uranus wrong, and the error doesn't stay contained to one planet in one solar system. It potentially propagates outward into how an entire class of world, scattered across thousands of star systems, gets modeled, interpreted, and understood. That's where this story goes next. Voyager 2 is still humanity's only spacecraft to have visited Uranus up close. That hasn't changed, and won't change for at least another decade. But something else has changed, quietly, over just the last few years. The tools available to study this planet from a distance have become powerful enough to start filling in some of the gaps that a single 6-hour flyby could never have covered. This matters directly to everything covered so far in this story. Every anomaly discussed in Part 1, every reanalysis discussed in Part 2 traces back to the same underlying limitation. One spacecraft, one afternoon, one set of instruments built with technology that is now, in some cases, older than the parents of the researchers currently studying that data. New instruments. Even ones not specifically designed for this purpose, offer a way to start testing whether Voyager 2's snapshot actually holds up, not by sending another spacecraft, which remains years away at best, but by pointing something already in space, already operational, back toward this planet and simply watching more carefully than anyone has before. The James Webb Space Telescope, launched in December 2021, and now roughly 4.5 years into its mission, has become an unlikely second window onto Uranus. It wasn't built primarily to study planets inside our own solar system. Its defining scientific goals involve galaxies at the edge of the observable universe and atmospheres of planets orbiting other stars. But pointed toward Uranus, at a distance of nearly 3 billion kilometers, its instruments turn out to be sensitive enough to see details no ground-based telescope, and in some cases not even Voyager 2 itself, ever managed to capture. The clearest demonstration of that sensitivity came in early 2025. On January 19th of that year, an international team of astronomers, led by Paola Turranti, a PhD student at Northumbria University in England, pointed JWST's near-infrared spectrometer at Uranus and simply watched continuously for 15 hours, nearly a full Uranian rotation. Their goal was to study the planet's ionosphere, the electrically charged upper layer of atmosphere where auroras form, and where the solar wind first makes direct contact with a planet's magnetic environment. It's exactly the same region of Uranus's environment that chapters 3 and 7 of this story have already spent considerable time exploring. Except this time, instead of a 6-hour glimpse from a spacecraft flying past at high speed, researchers had 15 hours of steady, patient observation from a telescope that wasn't going anywhere. What they produced, published in the peer-reviewed journal Geophysical Research Letters in February 2026, was something Voyager 2 could never have delivered: the first three-dimensional map of Uranus's upper atmosphere. Not a single snapshot, but a structured picture of how temperature and the density of charged particles change with altitude, tracked up to roughly 5,000 kilometers above the planet's visible cloud tops. This is the first time we've been able to see Uranus's upper atmosphere in 3 dimensions, Turenti said after the study's publication. The team found that temperatures in this region peak somewhere between 30 and 40 kilometers up, and that ion density peaks lower closer to 10 kilometers above the clouds, the kind of layered structured detail that a brief flyby moving too fast to gather more than a handful of readings simply has no way to capture. The same observation run also confirmed something researchers had suspected for years, but never measured with this level of confidence: Uranus's upper atmosphere is still cooling. Scientists first noticed hints of this trend back in the early 1990s, using ground-based telescopes to track subtle changes in the planet's temperature over time. JWST's 2025 measurements put a number on it. The upper atmosphere is now roughly 426 Kelvin cooler than it was when earlier measurements, including Voyager 2's own readings from 1986, were taken. That's an enormous shift for a planetary atmosphere to undergo over the span of a few decades. And it remains an open question exactly why it's happening, though it likely connects back to the same unresolved puzzle from Part 1. Something about Uranus's internal heat budget behaves differently than it does on the other giant planets. And nobody yet has a complete explanation for what that something is. There's a poetic detail buried in how this observation became possible at all. Uranus's extreme sideways tilt, the same 98-degree line that made Voyager 2's 1986 flyby so geometrically strange, the same tilt discussed all the way back at the start of this story, is precisely what gave JWST the opportunity to study the ionosphere the way it did. Because Uranus's pole was angled favorably toward Earth during this observation window, researchers could watch nearly an entire planetary rotation's worth of atmosphere sweep past in a single continuous viewing session, something that wouldn't be nearly as easy at a planet spinning more conventionally upright. The very feature that made this planet so hard to study properly in 1986 is now, decades later, helping scientists study it in an entirely new way. The ionosphere isn't the only thing JWST has found that Voyager 2 missed. In the years since Webb became operational, its instruments have twice caught sight of moons around Uranus too small and too faint for any previous telescope, or for Voyager 2's cameras to have ever detected. In November 2023, astronomer Scott Shepard, using ground-based telescopes in Chile, spotted a moon provisionally designated S2023U1, estimated at roughly 8 kilometers across, smaller than most cities. Then in August 2025, a team led by Maryam El-Moutamid of the Southwest Research Institute announced something even more remarkable. JWST itself, using its near-infrared camera, had captured a previously unknown moon in a series of 10 40-minute exposures taken back in February of that year. Provisionally designated S2025U1, the moon is estimated at only about 10 kilometers across, small enough, as planetary scientist Heidi Hammel put it after the discovery, that I could walk around this moon. It brought Uranus's confirmed moon count to 29, orbiting quietly at the edge of the planet's inner ring system, in a region so faint and cluttered with debris that it had simply gone unnoticed for nearly 40 years of study. Neither of these tiny new moons changes the central story of this episode by itself, but they matter for a reason that connects directly back to everything discussed so far. Voyager 2's single flyby wasn't just too brief to capture the planet's magnetic environment accurately. It was too brief, moving too fast, with cameras too limited by 1970s technology to see everything that was actually there. If a telescope sitting nearly 1 million kilometers from Earth pointed at a planet 3 billion kilometers away. Confined moons Voyager 2's cameras flew straight past without ever noticing. It raises an obvious question about what else might still be waiting unnoticed in that system. Moon's ring structures geological features on the far sides of Miranda Ariel and Umbriel that no spacecraft has ever photographed. JWST's relationship with Uranus actually goes back further than either of these moon discoveries. As early as April 2023, less than a year after the telescope became fully operational, astronomers released a striking image of the planet showing its ring system in far greater clarity than anything captured from the ground. 11 of Uranus's 13 known rings visible in a single frame, including the faintest, dustiest ones that typically require the most sensitive instruments to detect at all. That same image revealed something Voyager 2's cameras were never sensitive enough to properly resolve: a bright, seasonal cap of atmospheric haze sitting directly over Uranus's pole, currently angled toward the sun, with an unexpected, subtly brighter spot glowing at its very center. Nobody fully understands yet what drives that central brightening, or why it appears during summer and fades again once a pole rotates back into darkness. Another small, specific mystery layered on top of everything else this planet has kept from view. A follow-up image released that December pushed the detail further still, capturing bright atmospheric storms, several of the planet's smaller moons, and the full ring system together in one exposure, a level of simultaneous detail that ground-based telescopes, fighting through Earth's own atmosphere, simply cannot match. Each new observing run since has added incrementally to the picture: more precise ring measurements, better constraints on cloud features drifting through the atmosphere, and now, with the Turanti team's 2026 paper, the first vertical cross-section of the ionosphere itself. That question becomes especially pointed when you consider what else JWST has revealed about Uranus's rings since 2023. They aren't the neat, static structure Voyager 2's images seem to suggest. More recent analysis of Webb's imagery indicates the ring and dust system around Uranus is considerably more variable, and in places semi-continuous, than the tidy 9-ring picture handed down from the 1986 flyby. That detail isn't just a scientific curiosity. It's become a genuine engineering headache for anyone trying to design a mission that would actually fly close to this planet, because an orbiter attempting to thread its way between rings that turn out to be messier and more unpredictable than expected runs a real risk of colliding with debris nobody mapped in advance. Which brings this story to the mission at the center of everything that's come before it, the one spacecraft humanity has spent years planning to send back to Uranus, and the surprisingly rocky path it's had to travel just to reach the launch pad. Every few years since the 1970s, NASA convenes a panel of planetary scientists to produce something called a decadal survey, a document that ranks, in order, which missions the agency should prioritize over the following 10 years, based on scientific merit, feasibility, and cost. It's an enormously influential process. NASA has a long-standing practice of following these rankings closely, and a mission that lands at the top of a decadal survey tends to receive real institutional weight behind it, even if funding and politics can still slow it down. In April 2022, the Decadal Survey covering the decade 2023 through 2032 delivered a result that surprised even some of the planetary scientists who had spent years advocating for it. Ahead of a proposed mission to search for life at Saturn's moon Enceladus. Ahead of continued work on returning samples from Mars, the single highest priority large mission recommended by the entire survey was a dedicated orbiter and atmospheric probe for Uranus, a concept now generally referred to as the Uranus Orbiter and Probe, or UOP. It's worth noting that this wasn't the first time Uranus exploration had come up for consideration. A full decade earlier, the 2011-2022 Decadal Survey had also recommended a flagship-class mission to an ice giant, but ranked it behind what eventually became the Mars 2020 rover mission and the Europa Clipper, both of which went on to launch, while the ice giant recommendation quietly went unfunded. Lee Fletcher, one of the scientists who has spent years pushing for renewed attention to Uranus and Neptune, has said he started thinking seriously about ice giant exploration as far back as 2008, watching that first recommendation get deprioritized in favor of other targets. By the time the 2023-2032 survey placed Uranus at the very top of the list, rather than somewhere further down, it represented not a sudden new idea, but the culmination of roughly a decade and a half of scientists steadily building the case that this planet and its entire underrepresented category of ice giants had waited long enough. The reasoning behind that ranking connects directly to everything this episode has already covered. The committee explicitly cited the fact that ice giant-sized worlds appear to be extraordinarily common throughout the galaxy, based on the census of exoplanets astronomers have now cataloged, which means a dedicated mission to Uranus wouldn't just be answering questions about one planet in our own solar system. It would provide, in the words used by the survey itself, ground truth for understanding the single most common type of planet astronomers have found orbiting other stars. Lee Fletcher, a planetary scientist at the University of Leicester who took part in the decadal process, described his reaction to the ranking bluntly. "When I first read that recommendation, I feared I might be dreaming." The original plan called for the Uranus orbiter and probe to launch in 2031 or 2032, taking advantage of a specific favorable alignment of Jupiter that would allow the spacecraft to use that planet's gravity as a slingshot, cutting the total travel time down to roughly 13 years and arriving at Uranus sometime around 2044 or 2045. That timing wasn't arbitrary. Voyager 2 flew past Uranus during the planet's southern hemisphere summer, which meant it only ever saw one half of the planet and its moons properly illuminated. Scientists calculated that arriving before 2049, before Uranus's southern hemisphere slides back into spring, would let a new mission see the parts of this system that have simply never been lit for a spacecraft's cameras before. That plan, unfortunately, has already started slipping. A paper published in 2026 in the Planetary Science Journal, written by members of the Mission Concept team, including several scientists who worked directly on the original decadal proposal, laid out a series of obstacles that have emerged since the 2022 recommendation. First, current funding projections make the originally planned 2031-2032 launch window unrealistic, which means the favorable Jupiter gravity assist tied to that specific window would no longer be available, and Jupiter won't return to a useful alignment for a Uranus mission again until sometime after 2044. Second, the specialized power source the mission depends on, a next-generation radioisotope thermoelectric generator, the kind of nuclear power source required for a spacecraft operating so far from the sun that solar panels become impractical, has run into its own production delays. The first unit of this new generator design isn't expected to be manufactured until 2030, which doesn't leave enough time to produce and fuel the 3 units a Uranus mission would need in order to launch in the early to mid-2030s as originally hoped. And then there's the ring problem raised in the previous chapter. The same 2023 JWST imagery that revealed Uranus's rings to be more variable and debris-filled than Voyager 2's data suggested has added a genuine safety question to the mission's design. Whether a spacecraft attempting a close orbital insertion near the planet could do so without unacceptable risk of striking material scattered through a ring system that isn't as clean and well-mapped as engineers originally assumed. None of this means the mission is canceled, and it's worth being precise about that distinction. What it means is that the most optimistic version of the timeline, launch in 2031, arrival in 2044, a spacecraft in orbit around Uranus before this decade's end +1, is very likely no longer achievable. Researchers are now actively studying alternative approaches, different launch windows extending out through 2038 and beyond that don't depend on the Jupiter alignment at the cost of longer flight times, and newer still developing heavy-lift rockets, including SpaceX's Starship, being evaluated as potential replacements for the launch vehicles originally assumed in the 2022 study. Under some of the less favorable scenarios modeled after the original recommendation, without the Jupiter shortcut, a mission launched later in the decade could take as long as 15 years to reach Uranus. Arriving as late as 2053, nearly 70 years after Voyager 2's single flyby, and well past the window scientists had hoped for to catch the planet's currently unseen hemisphere in useful sunlight. The Uranus orbiter and probe, as currently envisioned, isn't the only concept scientists have proposed for returning to this planet, either. It's simply the one that carries the Decadal Survey's official endorsement, and with it, the best realistic chance of actually being built. In July 2023, a team at Johns Hopkins University's Applied Physics Laboratory floated an alternative concept called Perseus, focused more narrowly on studying the planet's plasma environment radiation and magnetospheric structure, essentially proposing to send a dedicated instrument specifically built to answer the exact questions Jasinski's reanalysis raised about whether Voyager 2's readings were ever representative in the first place. Earlier concepts floated in the preceding decade, with names like Oceanus and Quest, imagined similar orbiter missions on different timelines and budgets, none of which advanced past the proposal stage. For now, the Uranus orbiter and probe remains the mission with real institutional momentum behind it, even as its exact shape, launch date, and arrival time continue shifting in response to the practical constraints of budgets, hardware, and orbital mechanics. There's a small, almost charming detail buried in the mission planning that's worth pausing on, if only because it captures how much affection this strange little planet has earned from the scientists who study it. Because Uranus's moons are traditionally named after characters from the works of William Shakespeare and the poet Alexander Pope, some members of the planetary science community have floated the idea of naming the orbiter itself Shakespeare, with its accompanying atmospheric probe named Pope, a nod to the same literary tradition that gave us Miranda Ariel Titania and Oberon in the first place. Nothing has been formally decided. But it's a reminder that behind the funding tables and gravity assist calculations, there are researchers who have spent entire careers waiting for a second real look at this planet, and who clearly haven't lost their sense of wonder about it along the way. There's a certain dark irony sitting at the center of this chapter, and it's worth naming directly rather than glossing past. Everything covered in parts 1 and 2 of this story, the tilted magnetic field, the vacuum magnetosphere, the anomalously intense radiation, belts the solar storm reanalysis. The moons that may or may not host hidden oceans. All of it stems from the fact that humanity has only ever gotten one real look at this planet for a few compressed hours under conditions now understood to have been unusually distorted. The clearest way to resolve nearly every open question raised in this episode is a long-duration orbital mission, capable of gathering the kind of repeated, varied observations that let scientists distinguish a planet's typical behavior from a one-off anomaly, the same way Messenger's years at Mercury eventually did. And that mission, ranked the single highest scientific priority in American planetary science for an entire decade, is currently drifting further from realization with each year that funding, hardware, and political will fail to align. Amy Simon, a senior planetary scientist at NASA's Goddard Space Flight Center and one of the lead authors studying the mission's updated challenges, put it plainly in discussing why Uranus was chosen over a comparable mission to Neptune in the first place. Uranus ranked higher not because it's scientifically more interesting than Neptune, but because at the time of the decision, it was technologically achievable within a realistic decade, a calculation now being actively revisited as that achievability window narrows. For a channel built around documenting the universe as honestly as the evidence allows, this is worth sitting with rather than skating past. The story of Uranus, as this episode has told it so far, has largely been a story about how a single flawed dataset can distort scientific understanding for decades, and about the moment researchers finally circled back and caught the flaw. But catching the flaw in old data is not the same as fixing it. The only way to genuinely correct the record on Uranus's magnetosphere, on its moons, on whatever else Voyager 2's one afternoon there might have gotten wrong, is to go back. And going back, it turns out, is an enormously difficult thing to arrange, even when an entire scientific community agrees, unanimously, that it should be the very next thing humanity does. It's worth being specific about what the Uranus orbiter and probe, if it ever launches, would actually be built to measure, because the value of this mission isn't an abstraction. Every open question raised across this episode maps directly onto a piece of the mission's planned instrument suite. The orbiter component is designed for a multi-year tour of the Uranian system, not a single pass. Current planning calls for a science phase lasting roughly 4.5 years once the spacecraft arrives. Long enough to observe the planet's magnetosphere under a wide range of solar wind conditions. Calm days, disturbed days, everything in between, rather than the single possibly unrepresentative snapshot Voyager 2 was forced to settle for. That alone would directly answer the central question raised by Jasinski's 2024 reanalysis. Is the magnetosphere Voyager 2 measured typical of this planet, or was it genuinely an outlier? A mission that watches for years, rather than hours, can simply check. The orbiter is also planned to conduct repeated flybys of each of the 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, rather than the single distant pass Voyager 2 managed for each of them in 1986. That matters enormously for the ocean question raised in Chapter 5 through Chapter 7 of this story. Detecting a subsurface ocean by magnetic induction, the same method that has provided some of the strongest evidence for Europa's ocean at Jupiter, requires observing a moon's magnetic response across multiple points in its orbit as the surrounding magnetic field varies. A single flyby can't do that. Repeated passes can. If Ariel Miranda Titania or Oberon really do harbor liquid water beneath their icy shells, a mission built around dozens of close encounters, rather than one brief pass each, would be positioned to find out directly rather than continuing to infer the possibility indirectly from surface chemistry and orbital modeling. The way the JWST and Nordheim-led studies from Chapter 6 currently have to, then there's the atmospheric probe itself, the Pope half of that informal Shakespearean Pope naming idea. Current mission concepts call for the probe to separate from the orbiter and descend directly into Uranus's atmosphere on a parachute, measuring composition, temperature, and structure as it falls, layer by layer, through clouds no spacecraft has ever sampled directly. Voyager 2 never did this. Everything scientists currently know about Uranus's deep atmospheric composition comes from remote sensing, spectroscopy, radio occultation, telescopic observation from a distance, rather than an instrument actually descending through the clouds and measuring gas composition directly, the way the Galileo probe did at Jupiter in 1995. A direct atmospheric probe at Uranus would settle open questions about the planet's bulk composition, its ratio of heavy elements to hydrogen and helium, and potentially why its internal heat budget behaves so differently from Neptune's. The same open puzzle raised all the way back in part one of this story tied to Uranus holding the record for the coldest atmosphere in the solar system. None of these capabilities are speculative or exotic. They're standard instruments and standard mission architecture, similar in kind to what Galileo carried to Jupiter and Cassini carried to Saturn, proven approaches, not experimental ones. What makes the Uranus orbiter and probe remarkable isn't the ambition of its design. It's simply that nothing built this way has ever been sent to this particular planet before, and that the questions it would answer have been sitting unresolved for nearly 4 decades, waiting on exactly this kind of sustained, patient observation that a single flyby was never capable of providing. Consider the difference in kind, not just degree, between what Voyager 2 could offer and what a genuine orbital tour could offer. Voyager 2 gave planetary science a single photograph of a moving system, a magnetosphere caught mid-storm, 5 moons each glimpsed from one angle in one lighting condition, an atmosphere sampled from a distance during one brief pass. An orbiter doesn't just take a better photograph. It watches the whole film. It would see the magnetosphere breathe in and out as solar wind conditions shift across months and years. It would watch each moon rotate fully into view, season by season, rather than presenting one frozen face forever. That distinction, a single frame versus the full sequence, is, in a real sense, the entire argument this episode has been building since its opening question. There's also a broader scientific stake riding on this mission that goes well beyond Uranus itself, and it connects directly back to the point raised at the close of Chapter 9. If Uranus and Neptune genuinely represent the most common type of planet found orbiting other stars, and the exoplanet census gathered by missions like Kepler strongly suggests they do, then a spacecraft actually visiting one of them, measuring its composition and structure directly rather than inferring it from a distance, would give astronomers their only real ground truth for interpreting thousands of similar worlds scattered across the galaxy that will likely never be visited directly in any of our lifetimes. Every model used to interpret a sub-Neptune exoplanet's atmosphere, discovered by JWST orbiting some star hundreds of light years away, ultimately traces some of its assumptions back to what's actually been measured directly at Uranus and Neptune, the only 2 ice giants close enough for a spacecraft to ever reach. Right now, that foundation rests on a single afternoon in 1986, now known to have been unusually disturbed by a passing solar storm. A dedicated orbiter wouldn't just answer questions about one strange, sideways planet in our own solar system. It would recalibrate the baseline used to understand an entire category of world across the Milky Way. That's the scale of what's actually at stake in whether funding, hardware, and political will eventually align behind this mission. Not just curiosity about a distant, cold, blue-green planet most people rarely think about. A genuine gap in humanity's understanding of the single most common outcome of planet formation anywhere astronomers have thought to look. It's worth pausing here at the close of this chapter to take stock of exactly where this story now stands. Part 1 of this episode opened with a single flyby, its data trusted for nearly 40 years as the definitive picture of an entire planet. Part 2 uncovered the reason that picture was almost certainly distorted, a rare solar storm, compressing the magnetosphere at the worst possible moment, catching Uranus in a state present only a fraction of the time. This chapter has shown what modern instruments, pointed at the planet from a distance, are already starting to reveal on their own, and what an actual return mission would be built to confirm if it ever manages to launch. What remains is the question this entire episode has been circling since its opening line. If the version of Uranus we've carried in our heads for 4 decades was shaped by a few hours of bad timing, what does the truer version of this planet actually look like, and what does getting it wrong for this long actually cost us? That's where this story goes next and where it closes. Start again for a moment with the question this episode opened on. What if the strangest planet in our solar system isn't actually strange at all, and the only reason we thought it was broke down to a few hours of bad timing? By now, that question has an answer, though it isn't quite the clean, simple answer it might have sounded like at the start. Uranus is strange. That part hasn't changed. It really does tilt almost completely on its side, the only planet in the solar system that rolls through its orbit rather than spinning upright. It really does hold the record for the coldest atmosphere ever measured on any planet, colder even than Neptune, sitting nearly 1.5 billion kilometers farther from the Sun. Its 5 major moons really do carry canyons deeper than anything on Earth, cliffs that would take 12 minutes to fall from, terrain so mismatched and fractured that scientists still only half-jokingly call one of them Frankenstein's moon. None of that was ever the product of bad timing. That part of the strangeness is real, measured across centuries of careful observation, and it isn't going anywhere. It's worth walking back through the full shape of how this story actually unfolded, because each piece only really makes sense next to the others. It began long before any spacecraft existed, with William Herschel squinting through a homemade telescope in his garden in Bath in 1781, mistaking a planet for a comet, then a star, before slowly, over months of careful observation by astronomers across Europe, the truth settled into place. 200 years passed with almost nothing added to that picture. 5 faint moons, tracked one at a time across more than a century, and no confirmed rings at all until 1977, discovered essentially by accident, just months before Voyager 2 left Earth. Then came the single afternoon that this entire episode has orbited around. January 24, 1986, 5.5 compressed hours of observation, a spacecraft threading a bullseye trajectory dictated by a planet lying on its side. Cameras nearly ruined by a software fault fixed just 3 days before closest approach. What Voyager 2 found that day reshaped planetary science for a generation. A magnetic field tilted almost sideways to the planet's spin, offset a third of the way toward one edge, behaving nothing like the clean, centered fields at Earth or Jupiter or Saturn. Radiation belts 100 times fainter than predicted. A magnetosphere so empty of plasma that scientists took to calling it, half seriously, a vacuum. 5 major moons that should have been shedding water ions into that environment constantly, the way icy moons do everywhere else in the outer solar system, and weren't, as far as anyone could detect, which led directly to the conclusion that all 5 were geologically dead. That conclusion held, largely unchallenged, for nearly 40 years. What bad timing actually touched was something narrower, and in some ways more interesting, not what Uranus is, but what a single afternoon in January 1986 made it look like. Voyager 2 arrived at this planet during a 5.5-hour window. The only close look humanity has ever gotten, and it happened to arrive in the middle of a solar wind event violent enough to compress the planet's entire magnetosphere down to 1/5 of its normal size. Conditions researchers now calculate occur less than 5% of the time. Everything that made Uranus's magnetic environment look uniquely, almost impossibly chaotic compared to every other planet in the solar system, the vacuum-empty plasma readings, the second most intense radiation belts ever recorded around any world, traces back to that one badly timed encounter. Not fabricated, not wrong exactly. Just captured under conditions nobody realized, for nearly 40 years, were anything other than ordinary. Follow that thread, and it leads somewhere with real consequences. If the magnetosphere Voyager 2 measured was compressed and depleted by an unusual storm rather than permanently structurally that way, then the conclusion scientists drew from it, that Uranus's 5 major moons must be geologically inert, producing no measurable trace of activity, was standing on ground far shakier than anyone recognized. That single inference shaped 4 decades of textbooks, documentaries, and scientific assumptions about an entire family of worlds, and in just the last 2 years, independent evidence has started pulling in the opposite direction from 3 completely different angles. A magnetospheric reanalysis showing the empty readings may have been a temporary artifact of the storm. A James Webb Space Telescope study finding carbon dioxide and carbon monoxide ice on Ariel that shouldn't be able to survive there unless something inside the moon keeps replenishing it. And a separate orbital dynamics study proposing that ancient tidal resonances could have kept an ocean liquid beneath Miranda's chaotic surface, possibly to this day. None of that constitutes proof, and this episode has tried to be honest about that distinction at every step rather than overselling it for a more dramatic ending. Nobody has photographed an ocean under Ariel. Nobody has directly detected liquid water anywhere in the Uranian system. What exists instead is something quieter, and in its own way more interesting than a single triumphant discovery. A set of independent research threads, gathered by different teams, using different instruments across different years, all pointing in the same direction, all converging on the same uncomfortable possibility that the frozen, lifeless picture of these 5 moons might never have been an accurate picture at all. Layer on top of that everything modern instruments have added since, almost as a kind of correction running in parallel. The James Webb Space Telescope, watching Uranus for 15 uninterrupted hours in January 2025. Mapped the planet's ionosphere in 3 dimensions for the first time, something a 6-hour flyby moving at high speed could never have attempted, and confirmed the planet's upper atmosphere has cooled by hundreds of degrees since Voyager 2's own readings, a shift still without a full explanation. That same telescope has quietly found 2 moons Voyager 2's cameras never noticed at all, tucked into the planet's ring system, too small and too faint for 1970s hardware to have ever resolved. Even the rings themselves, once assumed static and well-mapped from that single 1986 pass, have turned out to be messier and more variable than anyone realized, variable enough, in fact, to complicate the engineering of the very mission now being designed to finally go back. And underneath all of it sits the plainest fact this whole story keeps circling back to. Every piece of that picture, the accurate parts and the possibly mistaken parts alike, comes from one spacecraft, flying past one planet, one time, 38 years before the reanalysis that started to unravel it. Uranus has existed, tilted and cold and strange, for 4.5 billion years. Humanity has looked at it closely for 5.5 hours. There's a broader lesson sitting inside this story, one that reaches well past Uranus, and it's worth drawing out explicitly rather than leaving it implied. Science doesn't fail when it draws a conclusion from limited data. It has to. Nobody can wait for perfect, complete information before saying anything at all. Not about a planet 3 billion kilometers away. Not about anything. Voyager 2's scientists in 1986 did exactly what good scientists are supposed to do with the data available to them. They measured what they could in the brief window they had and drew the most reasonable conclusions the evidence supported at the time. Calling Uranus's magnetosphere the most extreme in the solar system wasn't a mistake in 1986. It was the correct read of the only data anyone had. Where the story gets more complicated is in what happened next, or rather, in what didn't happen next. For nearly 4 decades, that single, necessarily provisional snapshot quietly hardened into settled fact. Documentaries stated it as established truth. Textbooks repeated it without caveat. The 5 major moons went from possibly inert, based on limited evidence, to simply inert, full stop, in the way that a hypothesis can slowly lose its hedges through years of confident repetition until nobody quite remembers it was ever provisional in the first place. That's not a failure of the original measurement. It's a failure of memory, a collective forgetting that a single data point, however carefully gathered, is still a single data point, and that treating it as a permanent verdict rather than an ongoing question is a choice, not a scientific necessity. This isn't unique to Uranus, and this episode said as much back in Part 2. Mercury spent decades known only through Mariner 10's 3 overlapping flybys before Messenger's years in orbit revealed a planet meaningfully different from the one those flybys implied. Pluto's entire scientific record still rests on a single pass by New Horizons in 2015. What makes Uranus a particularly sharp example isn't that this pattern is rare. It's that the gap is unusually wide and unusually consequential because ice giant-sized worlds appear to be the single most common outcome of planet formation, found anywhere astronomers have looked among the thousands of stars surveyed by missions like Kepler. Every model built to interpret those distant worlds leans, at some point, on what's actually been measured at Uranus and Neptune, the only 2 ice giants close enough for any spacecraft to ever reach directly. Get the baseline wrong, even by accident, even for defensible reasons at the time, and the error doesn't stay contained to one strange, sideways planet in our own solar system. It quietly propagates outward into how an entire category of world, scattered across the galaxy, gets understood. There's a kind of humility built into good science that this story illustrates better than most. The Voyager 2 team wasn't wrong to trust their instruments in 1986. Jamie Jasinski and his colleagues weren't obligated to go back and question 40-year-old data that everyone else had long since stopped examining. Both things can be true at once. The original measurement was sound science, faithfully recorded, and the conclusion built on top of it still needed revisiting, decades later, by someone willing to ask a question that had simply gone unasked for far too long. That's not a contradiction. That's closer to how science is actually supposed to work, when it works well, provisional, self-correcting, always a little uncomfortable with its own confidence, always ready to be told by new evidence that yesterday's settled fact was really just yesterday's best available guess. It's worth sitting, too, with how ordinary the mechanism behind this specific mistake turned out to be. This wasn't a story about faulty instruments, or bad math, or anyone cutting corners. It was a story about timing, about the simple, unglamorous fact that a spacecraft arrived during a rare solar storm instead of an ordinary week, and that nobody thought to check whether the week was ordinary until nearly 40 years later. If Voyager 2 had launched a few days earlier or later in its multi-year journey, if its trajectory had carried it past Uranus during one of the other 96% of weeks when the solar wind wasn't unusually disturbed, this entire episode might never have needed to exist. The most consequential fact in this whole story isn't a discovery. It's an accident, the kind of accident that's easy to overlook precisely because nothing about it looks like a mistake from the inside. There's a version of this lesson that applies well beyond planetary science, and it's worth naming plainly before moving on. Any single measurement of anything taken at one moment in time tells you what was true at that moment. It doesn't automatically tell you what's typical, what's permanent, or what's representative, and the gap between those things is exactly where a plausible-sounding conclusion can quietly harden into an inaccurate one, not through any dishonesty, but simply through the passage of time and the slow erosion of the caveats that should have stayed attached to it. A doctor taking a single blood pressure reading during a stressful visit to the clinic understands intuitively that one number on one day isn't the same as a diagnosis. Planetary science working with data points that cost billions of dollars and take a decade to gather doesn't always have the luxury of a second reading to check the first one against, which makes the discipline of remembering a measurement's limits rather than forgetting them the moment they become inconvenient all the more important. None of this should curdle into cynicism about what Voyager 2 accomplished, and it's worth closing this chapter by saying so directly. The spacecraft did something no human-made object had ever done and has never done since. It flew within striking distance of a planet nearly 3 billion kilometers from home, using computing power smaller than a modern digital watch, and returned data so rich that scientists are still actively mining new insight from it 40 years later. Not despite its limitations, but often because of them, using exactly the kind of careful, patient reanalysis that revealed the solar storm in the first place. A single flawed snapshot, examined honestly and revisited when new tools allow it, is still worth infinitely more than no snapshot at all. The failure here was never Voyager 2's. It was the slow, human tendency to stop asking whether a 40-year-old snapshot still deserved the weight everyone had quietly agreed to give it. There's a final layer to this lesson worth drawing out, because it applies just as much outside science as inside it. People do this too, form a single impression of someone, or something, in one narrow window of time, then quietly let that first impression calcify into a permanent verdict, long after the circumstances that shaped it have changed or turned out to be unrepresentative. A tense first meeting becomes, that's just how they are. A single bad experience with an unfamiliar place becomes a fixed, unrevisited opinion, repeated for years without anyone checking whether it still holds. Uranus's 40-year reputation as the most extreme, most chaotic magnetosphere in the solar system is, in a strange way, a planetary-scale version of exactly that pattern, a first impression formed honestly, under genuinely unusual conditions that nobody circled back to question until circumstances forced the issue. The universe, it turns out, is not exempt from the same basic error that trips up everyday human judgment. Neither, really, is the practice of studying it. What redeems the story in the end isn't that the mistake never happened. It's that someone eventually went looking for it, with no guarantee they'd find anything at all. JWST didn't know, when he started digging back through Voyager 2's archived solar wind readings, that he'd find a storm 20 times stronger than baseline sitting in the days before closest approach. He was testing a hypothesis built from experience at a completely different planet, willing to spend months of careful analysis on the possibility that decades of settled scientific consensus about Uranus might rest on nothing sturdier than bad timing. That's not a dramatic, cinematic kind of scientific heroism. It's slower and quieter than that, the discipline of returning to old assumptions, on the chance that something important got missed the first time, even when nobody is demanding you look. It's worth asking, before this episode closes, where else in the solar system a version of this same story might already be quietly waiting to be found. Every world visited by only a single spacecraft on a single pass carries the same underlying risk Uranus carried for nearly 40 years. The risk that whatever conditions happened to exist during that one narrow window got mistaken, understandably but incorrectly, for how that world always is. Pluto's global picture still rests almost entirely on New Horizons' one flyby in July 2015. Nobody yet knows how much its thin, hazy atmosphere or its surface features vary season to season, because no spacecraft has ever been back to check. Neptune has fared even worse than Uranus in one sense. It, too, has had exactly one visitor, the very same Voyager 2, on the very same grand tour, in August 1989, 3 years after the Uranus encounter, and just as brief. Whatever unusual conditions the solar wind happened to be producing that particular week have never been reanalyzed the way Jasinski's team went back and reanalyzed Uranus. It's entirely possible nobody has checked, yet simply because nobody has thought to ask the same question twice. That's not a criticism of the scientists working in these fields. It's closer to an honest accounting of how much of what humanity currently believes about the outer solar system rests on a remarkably small number of brief encounters, scattered across 5 decades, each one treated afterward as more definitive and more permanent than the data underlying it can really support. Every one of those single snapshots is a genuine scientific achievement. Every one of them is also, potentially, still waiting for its own version of a JWST, someone willing to go back, question the timing, and see whether the picture holds up. Voyager 2 is still flying. As of early 2026, the spacecraft that gave humanity its only close look at Uranus is roughly 143 astronomical units from Earth, more than 21 billion kilometers away, deep in interstellar space, well beyond the edge of the Sun's protective bubble it crossed back in November 2018. It has been traveling for nearly 49 years. Its radioisotope power source, the same plutonium-fueled generators that powered its cameras and instruments past Jupiter, Saturn, Uranus, and Neptune, has been slowly, steadily fading the entire time, losing a small amount of usable power every year since launch. Engineers at NASA's Jet Propulsion Laboratory have spent the last several years carefully rationing what's left, shutting off heaters, disabling one science instrument after another, borrowing reserve power from safety systems never meant to be tapped this way. All in the effort to squeeze a few more years of data out of a spacecraft that was never designed to still be reporting home half a century after it launched. One instrument, the Plasma Science Detector, was switched off in October 2024, Others are scheduled to follow. NASA's own engineers describe the goal, now plainly, as trying to keep at least one instrument alive into the 2030s, not because the spacecraft is expected to make another dramatic discovery, but because every single day it continues transmitting is a day of data from a region of space no other human-made object has ever occupied. A radio signal from Voyager 2, traveling at the speed of light, now takes over 19.5 hours to reach Earth. Send a message today, and by the time any reply could possibly arrive, the better part of a full day will have passed in silence. That's not a metaphor. That's simply the physical distance this spacecraft has covered since it launched from Florida in the summer of 1977, carrying, among its instruments, a golden record etched with the sounds of Earth, whale song human greetings in dozens of languages, a heartbeat music from cultures scattered across the planet it left behind, on the vanishingly small chance that something someday might find it and wonder who built it. Consider for a moment the strange asymmetry sitting at the heart of this entire story. Voyager 2 carries a message meant for whatever intelligence might one day intercept it in the depths of interstellar space, a deliberate, hopeful act of communication aimed at an audience that may never exist. And yet the spacecraft's actual, most consequential legacy turned out to be something almost the opposite. Not a message sent outward, but data sent backward toward the very civilization that built it, still being decoded, corrected, and better understood 4 decades after the fact. The golden record was built for a hypothetical listener who may never come. The magnetometer readings from January 1986 were built for scientists who, as it turned out, needed nearly 40 years and a completely different research question at a completely different planet before they were ready to hear what that data was actually saying. Ed Stone, who served as the Voyager mission's sole project scientist for 50 years from 1972 until his retirement in 2022, spent his entire career standing at the intersection of those two audiences, the hoped-for listener out among the stars, and the very real scientists back on Earth still working through what the mission actually found. He guided the spacecraft through all 4 of its giant planet encounters, including the Uranus flyby at the heart of this episode, before stepping down in 2022 and passing away 2 years later, in June 2024, at the age of 88. He never got to see Jasinski's reanalysis reach publication that November, 5 months after his death, never got to see the mystery he'd spent decades describing to the public, finally traced back to a single, badly timed solar storm. But the data he oversaw collecting, patiently archived and preserved for nearly 40 years, was exactly what made that discovery possible in the first place. In a very real sense, his most lasting contribution to this story wasn't the discovery itself. It was making sure there was still something left to discover, decades after anyone expected there would be. The people who worked on Voyager 2's original Uranus encounter in 1986 are, in many cases, no longer working in the field, retired or passed on in the decades since. Ed Stone, the mission's chief scientist for nearly 50 years, guided its exploration of all 4 giant planets before his own retirement from the role and death in 2024. Having spent a career watching a spacecraft, he helped build outlive every conservative estimate anyone made about its lifespan. The scientists now reanalyzing the data he oversaw, Jamie Jasinski at JPL, Richard Cartwright and his colleagues at Johns Hopkins, Paola Turrenti as a graduate student at Northumbria, represent an entirely different generation, most of them not yet born when Voyager 2 made its closest approach to Uranus. That handoff, quiet and largely uncelebrated, from the people who gathered the data to the people finally equipped to properly interpret it, is its own kind of continuity, proof that a scientific dataset carefully archived and made available can keep working long after everyone who originally collected it has moved on. Linda Spilker, the mission's project scientist, put it simply after the most recent round of instrument shutdowns. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be its last, but that day could also bring another revelation. There's something worth sitting with in the fact that the spacecraft responsible for this entire story is still out there, still faintly transmitting, roughly 19.5 hours away from Earth at the speed of light, growing fainter year by year. Voyager 2 is not going to fly past Uranus again. It's not going to correct its own 40-year-old data or resolve the questions its one brief visit left open. That work belongs entirely to what comes next, to researchers willing to go back through old archives with fresh eyes. To telescopes patient enough to watch a distant planet for 15 uninterrupted hours, and if funding and hardware and political will ever fully align to whatever spacecraft eventually carries the name Uranus Orbiter and Probe or Shakespeare, or whatever it ends up being called. Out past Jupiter and into orbit around a planet that has waited 38 years and counting for someone to come back and look again properly this time. If that mission does eventually launch, sometime in the 2030s, arriving at Uranus in the 2040s or later, it will do something Voyager 2 never had the luxury of doing. It will simply watch patiently, for years, the way a long-term relationship reveals things a single first encounter never could. It will see the planet's magnetosphere breathe in and out across dozens of solar wind events, calm ones and violent ones alike, and finally be able to say with confidence which behavior is typical and which was the exception. It will fly past Miranda, Ariel, Umbriel, Titania, and Oberon not once each but repeatedly, across different points in their orbits, finally testing directly whether any of them conceal the ocean's current evidence only lets scientists suspect. It will drop a probe through clouds no instrument has ever sampled from the inside, settling questions about this planet's deep composition that have remained open since before most of the researchers currently working on Uranus were born. Everything this episode has raised as an open question, a suspicion, or a converging body of indirect evidence that future mission is specifically designed to finally answer outright. Until that happens, the version of Uranus most people carry in their heads, cold, tilted, faintly green, its 5 moons frozen and silent, remains built substantially on a single afternoon, caught in the middle of a storm nobody knew was happening. That's not a reason to distrust everything science has told us about this planet. It's a reason to hold that knowledge the way good scientists already try to hold it, firmly enough to act on, loosely enough to let go of the moment better evidence arrives. What if the strangest planet in our solar system isn't actually strange at all, and the only reason we thought it was broke down to a few hours of bad timing? The honest answer, after everything this story has covered, is more layered than a simple yes or no. Uranus really is strange, in ways no accident of timing can explain away. But some of what made it look impossibly, uniquely strange really was an accident, a coincidence of bad timing that took 38 years, 3 independent lines of evidence, and one very patient space plasma physicist to finally catch. Somewhere out past the edge of the solar system, still moving, still listening, Voyager 2 carries on the small, aging messenger that started all of it, and the only proof, for now, that anyone has ever gotten close enough to see.